When we perform linear regression and evaluate our results, we are resting that interpretation on a set of assumptions. Let's dig into those assumptions and common violations of those assumptions. So our 7 core assumptions are that the betas in the model have a linear relationship to the dependent variable. The second assumption is that the expected value of the error term is 0. If we summed all of the values for the error term, we would expect the sum of those values to be 0. Our third assumption is that none of the predictor variables is perfectly related. Our fourth assumption is that the variance of the error term is consistent for all observations. Our fifth is that the error term is not correlated with our observations. The sixth is that the error term is not correlated with the predictor variables. And our seventh assumption is that the error term is normally distributed. The properties of ordinary least squares estimators that we rely on these assumptions. We like that these estimators are unbiased and they minimize variation. So by minimizing variation, we are taking the least squares, the least of the error sum of squares. If even one assumption is violated, we can't be so sure that these properties are maintained. We also know it interferes with the results of significant tests. So suddenly we're not so confident in our results. At this point, you might have noticed that most of the assumptions are based on the error term. For this reason, we can use the residuals or the observed error term to investigate the assumptions. Residual plots are especially helpful for identifying common assumption violations, so we're going to take a look at a few of them throughout this lecture. You can generate residual plots both in Excel and R. Residual plots are usually presented in one of 3 formats. Here is a residual plot that meets our assumptions. All points are randomly around 0, and no outliers pop out. If you start to see patterns, it's time to start getting concerned. So the fact is, most relationships out there are not perfectly linear, but it is an underlying assumption of the OLS model. If there is a nonlinear relationship, we often find a plot of the residuals looks like it's smiling or frowning. There are other types of regressions that can handle curves, so don't panic. It just means that maybe we need to try a different approach to address the data at hand. So in this model, age and happiness are evaluated. We see in the plot of the regression equation the line doesn't seem to be the best fit with the data. The residuals reinforce that idea. Nonlinear regression models can help, and that's what we're going to look at next. Multicollinearity is when 2 or more of your x variables are closely related to each other. When this happens, the significance of one variable versus another can be miscalculated or even have the wrong sign. And while an overall model might have great fit statistics, the individual predictors might not have much in the way of significance. So we can do a few things to fix this. We can drop one of the collinear variables, obtain more data, express variables differently, or in some scenarios, we might even just do nothing. Although, caution should be exercised if that's the approach that you choose to take. So this model aims to predict home values with household income, per capita income, and the percent of owner-occupied homes. The first model includes all 3 of those potential independent variables. Model 2 drops per capita income and Model 3 drops household income. Take a careful look at the independent or predictor variables in the models. What could be going on here? Are the results what you would expect? So we can do a few things in this scenario. We can throw out one of the variables, we can collect more data, or even do nothing. I mean, it is your model, after all. But we see that the significance and sign of the coefficient for per capita income changes when household income is included in the model, and that definitely suggests that multicollinearity could be a concern in this scenario. So this one isn't the worst. The coefficients are usually okay with the changing variability, but it still leaves us unsure as to whether or not we can use our standard errors and goodness of fit statistics. In the chart, you can kind of see how the distribution of residuals gets wider or fans out on one side. So that's how we can go about detecting this issue, and we can use robust standard errors as a remedy. When we have correlated observations, we run into some issues because we generally assume that our observations are uncorrelated, and usually this is a pretty safe bet. But we need to be especially careful for it in time series data. So if we think there may be serial correlation, we can plot residuals against the variable, usually an interval of time, to see if a pattern emerges. Here the residuals for a model estimating sales at a sushi restaurant are evaluated versus time, and we see a wave pattern. These patterns are a tip-off that something needs a little more investigating. And it is really difficult to include every possible variable that can explain some of the dependent variable in the model. And sometimes when we try, we end up with situations like multicollinearity on our hands, and it's a matter of choosing the lesser evil. And if it seems absolutely impossible to specify a model that's appropriate, maybe we need to consider another type of regression, maybe logistic regression or something like that. So these are some of the common violations that we run into with simple linear and multiple regression that conflict with our 7 core assumptions. I hope you found it helpful, and I'll catch you next time.